Let's solve this initial value problem. The first thing we note is that we can divide both sides by this 1 minus x squared, and we'll get a separable, since it's a separable differential equation, and we'll end up with 1 minus x squared dx dt equals 1. Now let's think about what would happen when we integrate both sides with respect to t. We know the left side becomes the integral of 1 over x squared dx dt with respect to t is 1 over 1 minus x squared dx equals the integral of 1 dt. Now the right side we can do no problem. That's just going to be the integral of 1 plus, or dt is just t plus c. Here as we think about integrating this, we see that it's not a good candidate for u substitution, and it doesn't fit some of our known integrals, so since it's a fraction, we can factor the denominator. Let's think about partial fractions. Okay, so we have the difference of perfect squares and then our denominator, so 1 over 1 minus x squared is equal to 1 plus x multiplied by 1 minus x. And by our partial fractions, we set this equal to a over the first multiplier in the denominator plus b over the second term in the denominator. And now our goal is to get rid of this fraction, so I'm going to multiply both sides of the equal sign by the denominator, so everything on this side by 1 plus x times 1 minus x. Everything here as well. Of course, that will cancel perfectly above and below. Where on the left side, we just get 1. And then as we think about this, remember, as you're multiplying through this denominator, it distributes across the addition, and the term that wasn't there is what's remaining because everything else cancels out. So that cancels, and we're looking at this equation. Now we want to find what are the values of a and b, and to do so, we could carefully choose x values that eliminate the other variables so that we can solve for that. So for instance, when x is equal to negative 1, I chose that because whenever we plug negative 1 here, 1 plus negative 1 is 0, this term goes away, and we just have 1 equals a times 1 minus negative 1 plus 0, so 1 equals 2a. That tells us a is 1/2. Similarly, if I choose x equal to positive 1, in this case, we're going to make this term disappear to 0. 1 minus 1 is 0. We get 1 equals 0 plus b times 2. b also equals 1/2. So the left side of our original equation through partial fractions becomes the integral of 1/2 times 1 over 1 plus x dx plus the integral of 1/2 1 over 1 minus x dx. And we know the right side was just equal to our t plus c. Now as there's a 1/2 on both sides, let's factor that out and then multiply to the other side, so we'll multiply both sides by 2. And we get our integral 1 over 1 plus x dx plus 1 over 1 minus x dx equals 2t, and I'm just going to leave it as the plus c. We'll have our constant absorb the 2 multiplier. Now as we integrate this, we know here with a quick u substitution on both, we would integrate this and we get ln absolute value of 1 plus x plus, and now here in this case, since our x is negative, we need to be careful as we do our u substitution. U is going to be 1 minus x. Our du will be negative negative dx. Now our term is positive, it's not negative, so that means we're really working with a, for this term, negative du over u as we integrate it, and that will give us a negative natural log absolute value of u. So in this case, we'll say minus ln absolute value of our initial term. Now here we'll find properties of logarithms useful. If logarithms of the same base, and these are both base e, are being subtracted, they can combine to a single logarithm where you divide the input. And now that we have that, let's solve for our dependent variable x's. So at this point, we're just going to use algebra to isolate x. I'm going to have e raised to the left side, which means that's going to be equal to e raised to the right side. E in natural log or inverse functions, so we get the input back as a result. And then we get e raised to the 2t plus c. Now here, remember properties of e, especially that's anything raised to a power whenever the power is being added. That means you had the original same base being multiplied, so the right side becomes e to the 2t times e to the c. And here we might call this our new constant b just for simplicity, because e to a number is some number, so we're just going to call it our b. And we had our original expression here. And now as we want to simplify this, let's multiply both sides by 1 minus x, our denominator. And we'll find, now as I write this out, I'm going to distribute out the right side. B e to the 2t minus b x e to the 2t. And now let's get all the terms that involve x's to one side, all the terms that involve numbers to the other. So I'm going to add this term to both sides, subtract this term from both sides, and we will get bx e to the 2t equals, plus x equals b e to the 2t minus 1. Let's factor out a common x from the left side. Divide both sides, and we get x is equal to b e to the 2t minus 1 over b e to the 2t plus 1. Now we did have our initial condition listed as that, so let's substitute that in. And if you would find it helpful, we even could have done that perhaps at this stage instead of after we already simplified. So our x is equal to 3 equals b e to the 0 minus 1 over b e to the 0 plus 1. That's going to give us 3 equals b minus 1 over b plus 1. Multiply both sides by b plus 1. 3b plus 3 equals b minus 1. We'll isolate subtracted b over, subtracted 3 over, and we get 2b equals negative 4. So b is our negative 2. So our final answer is negative 2, negative 2. Suppose that the fish population, P of t, in a lake is attacked by a disease at time t equals 0, with the result that the fish cease to reproduce. So our birth rate, beta, is 0, and the death rate, delta, deaths per week per fish, is proportional to 1 over the square root of the population. If there were initially 900 fish in the lake and 444 were left after 6 weeks, how long did it take all the fish in the lake to die? So let's translate the information we've been given so far. We know initially there were 900, so at 0 weeks there were 900 fish. After 6 weeks, it decreased and we were only at 401. Now we know our birth rate is equal to 0, and our death rate is proportional. So there's some constant multiplied by our 1 over square root of p to model this. So let's call our constant of proportionality k is k times 1 over square root of p, or delta is k times p to the negative 1/2. Now this situation will fit our general population equation that the change in population over time is equal to the births minus the deaths times the population. So for our case, we have dp dt is equal to, we have 0 births because of our disease, minus our constant, our death, times this. Now as we simplify this, we would get dp dt equals negative k times p, same base, so you can add the exponents. There's an implied 1 here. Negative 1/2 plus 1 is a positive 1/2. So this is our differential equation that shows the change in the population over time. And specifically, we want to know how long did it take for all the fish in the lake to die. To do that, we'll need to find an equation for the population, solve for all of the constants that come up as we find it, and then set that equal to 0 and find what weeks correspond to that. Now, as we look at this differential equation, we see that it's separable, so I could move the terms along p to the left side, and we get p to the negative 1/2 times dp dt equals negative k. Now here, let's integrate both sides with respect to t. This is just our polynomial. Integrating a polynomial, add 1 to the power and divide by it. Add 1 to the power of negative 1/2, and we get positive 1/2. Divide by that, we get 2 times p to the 1/2 equals negative kt plus c, as we integrate the right side with respect to t as well. Now, as we've done this, we see we have our constant of integration that appeared, and we had our proportionality constant. So in order to get an equation that works for us, we need to find out what are these two constants, and then we'll know how the population changes with respect to time. And to find these two constants, we'll need to use our two fixed points of information. Let's first use the initial value, because by plugging in 0 to t, this term will disappear, which will allow us to get down to an equation in only one variable. So using this information, we know 2 times the square root of 900 equals negative k times 0, 0, plus c. So c is equal to 2 times the square root of 900, which is 2 times the square root of 30. So our c is equal to 60. Next up, now that we found the value for c, we can plug in the population at week 6 to solve to get k by itself. So we have 2 times 4, 4, 1, all to the square root, equals negative k times 6, and that should just be a 60, that was a copying error, plus 60. Now the square root of 441 is 21, so we have 2 times 21 equals negative 6k plus 60. We'll subtract 60 from both sides, divide by negative 6, and we'll get that k is equal to 3. So our equation, we can fill in our k value, and we get 2 times the square root of p equals negative 3t plus 60. And now we want to find how long did it take for all the fish in the lake to die. So we set our population equal to 0. 2 times the square root of 0 equals negative 3t plus 60. 0 equals negative 3t plus 60. And we can solve this and see that it would take t equal to 20 weeks for the fish population to go to 0.